Okay, here's the fifth video in chapter 11, hopefully the last one on valence bond theory. Now, in previous chapters, I've introduced the SP hybridization. Again, in passing, introduced the SP3D and SP3D2 hybridization for the 5 and 6 groups. I want to kind of circle back and just kind of summarize this or look at this before I introduce the next subject. So, in the four molecules that we talked about in the last video, which is methane, ammonia. Actually, I wasn't. I think I talked about carbon tet, but carbon tetrachloride and methane have the same basic shape, where instead of hydrogen, it just has chlorine. But I talked about these three, and one thing that is interesting about all three is that in each case I end up using a molecule that had single bonds. Remember, in chapter 10, an awful lot of the bonds we encountered were double bonds, or sometimes via resonance. They were kind of they had a bond order somewhere between 1 and 2, based on the resonance forms. But in all these examples, the bond order is 1. They're just single bonds. Okay. So and the orbital theory, the VB theory that involves the hybridized orbitals did a pretty good job of explaining how the regions where the electrons were overlapped could be explained geometrically, and that geometry follows the shape that we observe and that we predict from VSEPR theory. Okay. Well, what about double bonds? Haven't talked about double bonds yet. So how would that work? So let's actually turn our attention now to that, and you'll see that it actually is well, you'll see what happens. Now, one thing I want to mention from a terminology standpoint is that when we talk about in this orbital theory, in this VB theory that involves orbitals, the bonds that we talked about that were end to end, basically a p-like orbital, whether it be a hybrid or a p, when it overlapped with another atom's p orbital, it was always done kind of end to end. So it was like along the x-axis, or along the y-axis, or along the z-axis, and the orbitals actually kind of overlapped along the loopy side of these things, kind of end to end. That type of bond that's formed is known as a sigma bond. Again, it's just the terminology that you use, but the bonding that's done end to end from along those orbitals is known as a sigma bond. And what you'll see is that that's synonymous with a single bond, or it's actually all of the bonds that I'm showing here on these three compounds all involve sigma style bonds, meaning those bonds involve an end-to-end overlap of orbitals. But what happens when you have a double bond? Well, it turns out a double bond, and I'm going to kind of jump to the answers for a second, but a double bond, like in ethylene, the double bond between the two carbon atoms in ethylene, one of them is a sigma bond, and one of them is something else. And I'll leave that to what we conclude with. But one of them is one of these sigma bonds, and one of them is something else. Okay, so let's look at this. Let's take this apart from an orbital standpoint. But first, I want to kind of tell you from an experimental observation. What we know is, and in fact this even falls out of V-separate theory, is if you look in V-separate theory, it would show that focusing on one of these carbon atoms, this carbon atom is bonded to 1, 2, 3 things. It's basically an AX3. Okay, it doesn't have a lone pair, so you don't put an E on there. And this is actually one of the things I'm not even sure if I emphasize much, but the fact that it's double bonded to C doesn't really matter. It's just this bond to C counts as one of the 3 atoms that's bonded to carbon. Okay, so the shape with respect to this carbon is AX3, which is planar, trigonal planar. Okay, similarly, the shape with respect to this carbon atom over here is also trigonal planar, which essentially means that this is all now V-separate theory, but you'll see that the VB theory that's based on orbitals will agree with this as well. But what this means is the ethylene molecule, the shape of the ethylene molecule is actually planar, because this carbon and its three entities are in one plane, and this carbon and its three entities are in one plane, and they happen to be in the same plane because they're bonded together. So ethylene the ethylene atoms make up or all lie in a single plane. All right, let's see if our orbital model can somehow explain that. All right, where's my eraser? Lost it, as usual. Okay. I'll redraw ethylene here and give myself some more room. Okay, so let's look at the orbitals for one of these carbons. It turns out you'll see that the other carbon is kind of the same. Actually, I could probably do both carbons anyway. But let's look at carbon, and which we know again has a 2s and it has two p's. And what we're going to do is we're going to hybridize these to form 1, 2, 3 bonding groups, okay, and then one left over. So I'm going to be using sp2 hybridization. Remember I talked about this when I talked about boron, I think. sp2 hybridization. And so the 4 electrons that carbon has, valence electrons, will fill 1, 2, 3, and one of the 2p that's unhybridized. All right? And what you'll see then is this carbon will actually use one of these sp2 hybridized orbitals to bond with the hydrogen, another to bond with the other hydrogen, and the third one to bond end-to-end with its neighboring carbon atom. So all of those bonds are I hate to get this phone. I'm gonna ignore that. Hopefully the recorder doesn't come on. It's going to use the third one to bond end to end with so these 3 hybridized orbitals are going to bond end to end with. Give me a second here. I can't pause this recording. Good. All right, no message. So the 3 hybridized are used for 1, 2, 3, all the sigma bonds, and there's one p orbital left over, and you'll see that the other carbon, of course, is identical. So each carbon essentially will form these 3 bonds, but each of them has a 2p orbital left over. Okay, now think about p orbitals. Remember the geometry of p orbitals is they're in 3 different dimensions. There's x, y, and z. The way I've kind of drawn this is that the p's that I've hybridized, the 2 p's that I've hybridized, are really the y and the x shapes because they fit in this plane. The last one is the z direction, okay? And so in the z direction we have this last p orbital. What that means then is that the carbon, each of these carbons, actually has an orbital that extends up in the z direction. I know it kind of looks like I'm just drawing in the y, but I have a hard time depicting that third dimension. But picture this loop that we have here as being in the third dimension. What happens is the second bond, the double bond, instead of it being end-to-end overlap, this overlap now kind of extends as an overlap between the two. And let's see if I can probably draw. I'll try to draw this a little bit better. I'm still not showing them overlapping, but imagine that the center of these 2 clouds is our carbon, or each of our carbon atoms, which again have bonded with 3 other things in the other 2 dimensions, in the plane of the other 2 dimensions. The double bond essentially is an overlap of these 2 orbitals. So the z direction orbital of one carbon overlaps with the z orbital of the other carbon, and they form kind of a, mathematically again, they form kind of a region, a shared region of density. That is, instead, again, it's not end-to-end overlap, it's kind of side-by-side overlap. It's kind of overlapping two loops like this, side by side, and not end-to-end, which is what we normally see, okay, in the sigma bonds. Okay, this side-by-side bonding that forms is known as a pi bond. So instead of a sigma bond, it's called a pi bond. And again, it is a bond that's formed between unhybridized p orbitals in this example. And those p orbitals line up geometrically to overlap side by side. So in the case of ethylene here, they overlap in the z dimension, so that the rest of the sigma bonding happens in the xy plane. That's why it's still a planar shape of the molecule. And it has this extra kind of rigidity, I would call it, of this bond formed in the z direction. And that's actually very important too. Maybe I will have some final comments about rigidity in the next video, and that's actually where I'll also introduce. Now let me carry on here. I'm going to try to finish this rigidity thing. So that actual pi bond actually kind of constrains the carbon bond a bit more. Now, this is something that we never really talked too much about. I think I mentioned it one time when I talked about single bonds being able to bend and stretch and rotate, and there's energy effects, of course. In order for this bond to stretch, for example, it needs to absorb a photon of a certain amount, etc. Now, it turns out when you have, and this is true for all kind of single bonds, and single bonds are a lot less restrictive or constrictive of the atoms, meaning those bonds can bend, stretch, and they have a lot of degrees of freedom to move. When you add in a pi bond, or for that matter, when you add in a second pi bond, which I haven't talked about yet, but there's an example that covers it, then the degrees of freedom, degrees of motion of these atoms becomes more rigid, a whole lot less degrees of freedom to move. And you can think about this in terms of the fact that if the carbon atoms are bonded in the plane, then they have this extra kind of attachment at the z direction. It's a lot more rigid. It can't twist like it used to, because in twisting it would end up breaking or greatly bending the bond that's formed on the side by side. Okay, so the key takeaway here is that when you have double bonds or triple bonds, the degrees of motion are much more restrictive, and for that matter, the bond is much stronger. And we've seen this. We've talked about it too. Is that when you have a double bond or a triple bond, it's stronger, meaning it takes more energy to break it, and that kind of makes sense because you have more electron overlaps here, like we're talking about. The only pointer I'll make on the acetylene example, the triple bond, is that instead of it being sp2 hybrid, it's basically an sp hybrid with two unhybridized p orbitals. So in the case of acetylene, the single bond, so acetylene actually looks like this. One of the sp hybrids is bonding to the H, the other is the sigma bond to carbon, and then the other two p orbitals are used for the first and second pi bonds. And as you can imagine, those pi bonds are going to happen, one's going to happen in, let's say, the z direction, the other's going to happen in the y direction, which essentially means that this molecule is going to be linear in the x direction. Okay? Ponder that one, and we'll discuss it if you got some questions. Okay, I think that's all I want to cover about VB theory, valence bond theory. The next video is going to go on to the second theory that we'll talk about next.